We left last time, right, where you were supposed to finish the one problem at the end of that paper, right? The one on driving under the influence and not driving under the influence. You all have that finished? Okay. You got it finished? Awesome. Okay. Now the key to this was what? Writing down probability of DUI versus the probability of no DUI, correct? And it helps when you write it down, right? And we don't have to have really long verbose sentences in there. You're just trying to be concise, right? DUI, no DUI. Okay. We were told in the problem that the probability of a DUI was 0.29. So the probability of no DUI is got to be 1 minus 0.29, which would be 0.71, correct? Okay. So the first question says, what's the probability that all three have driven under the influence? What's the probability all three are DUI? That's a DUI and a DUI and a DUI, correct? And what do we do when we say and? Multiply, that's right. Very good. All right, so you should have ended up with the probability of all three being DUIs as 0.0244, right? So it's 0.29, 29% raised to the third power, because we're multiplying it by itself every single time. Yeah, did y'all get that? Okay. And if you didn't get it, do you see why you didn't get it maybe? Okay. Now the second says, what's the probability that at least one has not driven under influence? So what's the probability at least one no DUI? What's the probability at least one no DUI? Remember when we talked about at least, we said the way that we calculate those is by taking the complement, right, of the opposite in essence, right? So when I think about at least one no DUI, then that's going to be 1 minus the probability of a DUI. I used a tree on this to get my brain processing it. All right. A lot of people don't need that. But if you have a hard time kind of visualizing what it is, you could make a tree. Most people don't need it, but sometimes I need that as just a kickstart to get my brain figuring out what we were talking about. Remember, when we had the at least, it was where our tree grew and we had that one branch that didn't have anything on it, right? It didn't have the at least one portion we were talking about. So that's why it's 1 minus 3 DUIs. So we end up with 0.9756. Okay? So far, so good? Good. How about the next one? What's the probability that none have driven under the influence? So what's the probability of no DUI? That's no DUI and no DUI and no DUI, which we just said we multiplied for, right? All right, so that would be probability of no DUI is 0.71 to the third power, or in other words, what do I have up there? 0.3579, is that what you all have? You did that? Yeah? Okay. And then the last problem, what's the probability at least one no DUI? This is the same problem that we had in part B. At least one no DUI means, at least one DUI. That's what I should have said. What's the probability at least one has driven under the influence? So what's the probability of at least one DUI is 1 minus no DUI. All right, and we have 0.6421, I believe. Okay. I know that one's hard. Those are hard. The at least and the, when we're thinking of it that way, it can get a little confusing. I understand. But just kind of got to keep working at it. Now, I put in the back of the room the paper that we're going to be using today when I came in. So if y'all all go back and get it. And actually, we're going to start chapter 6 today. So the paper that I put back there for you has the problems that we are, in essence, that we are going to work, that I'm going to work, okay? We're also going to need StatCrunch, so if you want to make sure that your computer boots up, you don't need it right away, but make sure that you're logging in and you're getting that kind of set up, because we're gonna kind of intro this a little bit. So chapter 5 was our chapter on probability. And for the most part, we don't really find probability like what we're talking about, these at least and all that kind of stuff. Mostly as we move through the rest of the chapter, as we move through the rest of the semester. But we need to understand this idea of probability as we move forward, which is why we take a little bit of time to kind of pause and talk about it. So today, what we're going to talk about are discrete random variables. We're going to use probability in its concept to talk about it today, but we're kind of moving away from that, what we did in chapter 5. Now, discrete variables were a special kind of variable, right? They were a special kind of quantitative variable. Remember that? So discrete variables were what kind of variables compared to continuous?
Ones that you can count.
Ones that you can count on your fingers. I think of them as integer values, right? Whole numbers in essence, okay? They don't have to be whole numbers, but they're just ones that you would normally count, all right? And what we're going to talk about, so we're focusing on them today. And what we're going to talk about is are these variables and the fact that we have different outcomes with these variables. So probability models for random variables, where random variables are the numerical measure of outcome to a probability experiment, okay? And rather than listing the specific outcomes of each experiment, like a heads or a tails, we list the number of heads obtained in 3 flips of the coin. All right, so that's kind of the idea of where we're going with this. So we want to understand, we have a couple of terms here. We want to understand that a random variable, when I talk about a random variable, all right, that we're going to be represented by X, that would be typical, okay? Random variable X, it has a single numerical value. This is what would be determined by chance, okay? We kind of think of it as like our outcome, all right? Then we have the probability distribution, which is really just the probability of X. All right, remember, we talk about probabilities as being capital P of something. We're going to learn in the next couple of chapters, we've got 2 more P variables we add to this. So it's important we understand capital P is always going to indicate probability. Okay, and our probability distribution is really just our probability for those events we had happening. All right, and you'll see that we are really fairly familiar with this concept. It's just we're kind of renaming it, I suppose, or reevaluating it. We know what a discrete random variable is, and we'll move into later on a continuous random variable. Okay, so when we think about this, we have our probability distribution, right? Our probability model. Our probability distribution has 2 requirements. The first requirement says that the sum of all probabilities equals 1. So this E here, this is a capital Greek letter sigma. It indicates to sum, to add things together. And it just says that the sum of all my probabilities have to equal 1. Is that any different from the rules of probability that we talked about last week? It's the same thing, right? Okay. Then the next rule for our probability distribution model says that each probability must be between 0 and 1, including 0 and 1. Right? So we have our inequality symbols here that have the equal sign underneath them, indicating that it's also an equality symbol. So the probability of our model, right? The probability of each individual component or outcome, I should say, has to be between 0 and 1, but it can be 0 and it can be 1. Again, is that any different from what we talked about as far as our rules for probability last week? It's the same rules. Okay, so this should be comforting to you. You're not learning anything new about probability. We are just framing it now in terms of a probability model, which you've already seen. So how do I go about working with this model? All right. The first thing we're going to use an example to kind of be able to understand this, discrete variable and so forth. And we're going to do it using a game. Most of us know how to play games. And if you think about any game out there, all games have some sort of expected outcome and the likelihood that you win versus losing. Okay. We're going to do it in terms of like dice rolling. Okay. I think, isn't there a dice game? It comes in a long tube and it's like a bunch of different colored dice. To start with a B or something. I mean, it's not long.
I don't remember, but I do have that at home.
So there's lots of dice games out there, and there's ways that you win at the dice game, ways that you lose at the dice game, right? For most games, yes, you agree with that? Okay. So I need some help from you all this morning so that this is clear enough for us. And the game that we're going to play says that there's 3 outcomes. All right, we're going to roll 2 dice. And if I roll a 7, then I'm going to win $1. So if I roll a 7 out of these 2 dice, I win $1. If I roll a 2, 3, 4, 10, 11, or 12, any of those 6 values, right? If I roll any of those 6 values, I'm going to lose $1. And then if I roll a 5, 6, 8, or a 9, I don't win or lose. It's called a push. Okay, so I'm not going to win my $1. I'm not going to lose my $1. Nothing happens. Okay, so there's 3 outcomes: a win of $1, a loss of $1, or no gain. Okay, we have 3 outcomes. Now, each of these outcomes has an associated probability. Did we not learn the other day that there was a probability to rolling a 7, right? All right, so on your papers, I want you to write down, let's see. So we have a win, and that's if I roll a 7. I have a loss. That's if I roll a 2, 3, 4, 10, 11, 12. And I have a push if I roll 5, 6, 8, or 9. Okay. Now, how do we determine what the probability is, or what's the likelihood of rolling a 7? How do I determine the probability of rolling a 7? How do I find that?
7 divided by 12?
No.
Or would it be 1 divided?
No. But at least you guessed, right? You're trying. I appreciate that.
I know that ones of making, how you can make 7. Count them up.
And divide it by what?
All the options.
all the outcomes, right? Remember, there it is. Remember that? Okay, so if I want to know what the probability is of rolling a 7, there are how many ways? These are all the outcomes of rolling 2 dice, right? How many ways can I roll a 7? Right, does everybody agree that it's 6 ways to roll a 7? Yeah, so we have a 1 and a 6 and a 1, a 5 and a 2, a 4 and a 3, a 3 and a 4, a 2 and a 5, and a 1 and a 6. Remember that the 6 and the 1 and the 1 and the 6 count as 2 separate rolls, right? As 2 separate outcomes. Yes? Remember why that happens? It's kind of easier if you think of them in different colored dice, right? That kind of helps. So there's 6 ways for us to roll a 7. We did this problem actually on that day. Out of how many total how many total outcomes are there? There's 36, right? So the picture here shows 36 possible outcomes. So 6 out of 36 ends up being 0.17 if I round it to the nearest 2 decimal places. Okay? All right. Now, what if I want to know what the probability is of a loss? How do I find the probability of a loss? What constitutes a loss? If I roll a 2, do I lose?
Yeah.
If I roll a 3, do I lose?
Yes.
If I roll a 4, do I lose?
Yes.
You see where I'm going with this? Okay, so how do I find then what the probability of a loss is?
Total possibilities of those numbers.
So it's the probability of a 2, or a 3, or a 4, or a 10, right? What am I saying when I say or? What operation do? I add, right? So it's a 2, or a 3, or a 4, or a 10, or 11, or a 12, right? Okay, and so when I find out what the probability of a 2 is, I add that to the probability of a 3, and so on. Okay? Okay. So I want y'all to figure out what the probability of a 2 is, a 3, the next one, a 4, a 10, 11, and a 12. Coming back to you. You got 2 seconds. Okay? Tell me, with the dice that are showing up there, what is the probability of the values I just told you? So just going back. We've got 2, 3, 4, 10, 11, and 12. It would be easier if we just wrote it as a fraction, by the way. Okay, so I'm looking for probability that I roll a 2. I know y'all can't see this over there, but somebody can. What's the probability of a 2? 1 out of 36. Give it to me as a fraction, all right? So I've got 1 out of 36. Everybody see that? 1 out of 36. Probability of a 2. There's only one way to get a 2, right? A 1 and a 1. Okay. How about the probability of a 3? How many ways can I get a 3? 2 ways, right? So I've got 2 out of 36. Are y'all writing this down on your paper? Good. Next row, back there on the back. How many ways can I get a 4?
3 out of 36.
3 out of 36. All right. All right, moving to the back row over there. How many ways can I get a 10?
3 out of 36.
3 out of 36. How many ways can I roll 11?
2 out of 36.
Good, 2 out of 36. And then last but not least, how many ways can I roll a 12?
1 out of 1.
1 out of 36. All right, so we know already that if I have a common denominator, all I have to do is add up the top, right? Which in essence is what we were saying. So 1 plus 2 plus 3. So I've got 3, 6, 9, 12. 12 out of 36, right? If I add all those numerators up. So the probability of a loss is going to be 12 out of 36, or in other words, 1/3, 0.33. Okay, 12 out of 36 is 1/3, which would be 0.33. So the probability of a loss is 33%. The probability of a win is 17%. Okay, do we understand where these numbers came from? Okay, so instead of me writing all of this down, I'm saying the outcome of me playing my game, the potential outcome of me playing my game is I can win, I can lose, or I can get a push. So to win, I only have to roll a single dice, right? There's only one way for me to win. But if I lose, I could lose 6 different ways, can't I? Okay, and that's where that probability comes from. And then I have another probability, and do we need to work through the probability of a push, or do y'all understand where this is coming from? It would be the probability of a 5, probability of a 6, plus the probability of an 8, plus the probability of a 9. Okay? Y'all know that? Y'all see that? All right. So I'm just going to tell you then that these are the probabilities for each of those outcomes that we were talking about, right? These are the probabilities for the outcomes we were just mentioning. The outcome of my game, and it's, in this particular case, what happens when I win, right? What happens when I lose, and what happens when I push. If I win, I get $1. If I lose $1. If I get a push, I get nothing, right? It's neutral. And so for each of these 3 possible outcomes, there is an associated probability. The variable that's changing in each of these outcomes is the value of our loss, or the value of our win, or the value of the push, right? That's what's changing. That becomes the variable. And in each of these, again, we have our probability that's associated with each of those outcomes. Do you all understand that? Okay, so that's kind of the setup. Now, if we were to play the game, say 1 time, we would have some outcome, right? If I play the game again, we would have another outcome. The outcome may be the same, it may be different, right? When you're playing this game, you're going to get all sorts of outcomes. If I wanted to maybe come up with an expectation, how much do you think I'm going to win on average if I played this game? Right? How much would I win on average if I played this game? That's what we are talking about when we think about expected value. So the mean or the average of our random variable represents what we expect to happen in the long run. So let's say we played the game 10 times, right? I could add up my winnings, divide it by 10, and I would have an average winning, wouldn't I? Yes? If I played the game 10 times, added up what I won and what I lost, divided it by 10, I would have an average winning for the 10 times I played. That's what the expected value is talking about. It's the average, the mean of our random variable and what we expect to happen in the long run. It's called our expected value. Now notice how we are symbolically representing this. So our mu of x, right? Mu represents mean of our variable x. That's how we read this, mu of x, all right? Is equal to what we are defining as our expected value. But to find the expected value, what did this symbol right here indicate again? Add to sum. So what we're going to do is we're going to take the sum of the outcome x times the probability of that outcome and add them together. That's pretty much what we would do if we were to play the game as well. So this is the formula that you need to make sure that you write down in your worksheet that we have there, okay? Now, let's figure out if this was our game, what we would expect to have happen for an outcome, okay? So, I have this table that I've pretty much already set up for you, all right? And this is what we would consider. This part right here is what we would consider our probability model, where we have some outcome and its respective probability. And if I follow along with the formula that we just wrote up there, what I need to do is I'm going to move to the next, I'm going to create a column over here on the very far right, and I'm just going to take each of these columns and multiply them together. In other words, I'm going to take 1 and multiply it times 0.17. I'm going to take -1 times 0.33 and 0 times 0.5. So I would have 0.17, -0.33, and 0 when I multiply those together. Now, what does the formula tell me to do? Once I've multiplied them, I'm going to sum them. I'm going to add them all up, right? I'm taking the sum of this product here. So 0.17 plus -0.33 ends up being what?
-0.16.
All right, that's right. Did you all come up with -0.16? That is our expected outcome. And what does this mean? This is saying, remember that I can roll a dice, and if I won, I got $1, right? If I won, I got $1. If I roll the dice and I lost $1, right? So what if I stayed at, let's say, this game, and I sat here and played it a gazillion times? What would the net profit or loss be, right? When I got up and quit playing the game? What is it? Don't just tell me it's -0.16. What does it mean?
It means you'll lose money.
How much? That's right, I will lose money. How much am I losing? Not $16. Not 16%. 16 cents. Right? 16 cents, 0.16. Okay, that's the average. If I only won $1 or I lost $1, right? Those are my two values plus 0. Okay. On average, I would walk away losing 16 cents. Okay, on average. Think about that. That's if I walked away. The better example or an additional example would be, remember me talking about the casinos and how the house wins? Every game has an expected value. And that expected value would be something like this, right? That if you're playing the game, you're going to lose, okay? And the house is going to win. The casino is going to win. They know this, all right? Does that mean if you walk in and you sit down at a slot machine, or you sit down at a blackjack table or whatever, does that mean you won't win some? Right? You probably will win, right? But on average, if you stayed at that spot, playing that game over days and days and days, you're not gonna win. The average outcome, right, of your endeavor there at the table or at the slot machine is gonna be that you lost. On average, you will come away losing in essence. That doesn't mean it always happens like that, right? Because they wouldn't have people that went to Vegas, right? But Vegas knows that on average, or casinos know that on average, when you're talking about a gaming thing like this, they are going to end up being the winner in this multi-billion-dollar business, okay? So the expected outcome says, just like when we think about probability, right? The probability of me flipping ahead is 0.5, right? 50%. But I don't always get it half the time, right? We know that if we repeated that process of flipping the coin, eventually my outcomes would get to be about 50%, right? That's the same thing for this. We're suggesting that over the long run, if you played the game as it's stated here on the screen, you would on average lose 16 cents. That's what we are looking at when we think about expected outcomes. We're trying to figure out, if I know that there's a probability associated with these outcomes, what is my average over the long run? Okay, that's what we're finding. All right, let's look at the next one. It really should not be gaming. It should be, I like to think of this one as more fixer-upper. I should call it fixer-upper. All right. So Sean and Maddie purchase a foreclosed property for $50,000 and spend an additional $27,000 fixing it up. They feel that they can resell it for $120,000 at a probability of 15%, 0.15. Okay, they could sell it for $100,000 with a probability of 0.45. They could sell it for 80 at a probability of 0.25 and 60 with a probability of 0.15. So they know they can sell it, but they don't really know what the sale price is going to be. They just know that there is a probability associated with each of these sales prices. So the variable that's changing in this sentence or in this scenario would be the sale price, right? The sales price is the variable that's changing. And we need to figure out or write down what's the probability associated with each of these variables, or yeah, with each of these sales prices. Okay, so when I think about the sales price, I have $120,000 at 0.15, $100,000 at 0.45, 80 at 0.25, 60 at 0.15. Now, what do we know about this value right here? What should these values all add up to be? What should those probabilities all add up to be? 1, right? They should all add up to be 1, and no probability in that statement can be less than 1, less than 0, or greater than 1, correct? All right, now I want you all to multiply the sale price times its probability, and let's record that in the column on the right. All right, did you get 18, 45, 20, and 9,000 for the results of the product? Okay. 18, 45, 20, and 9,000. The result of multiplying those together. Now, if I add them all up, because that's the next part of this, right? I'm going to take the sum of that. And what do we end up with? So $92,000 is the expected value. What does that mean in terms of this question? What's the interpretation of that? What does that number tell us?
They're looking to profit $92,000.
No, they're not gonna profit. We'll have to do a little bit more, but what else about the 92?
Resale value.
It has to do with this resale, that they think that they can sell it. What else though?
The average resale.
They would expect the average resale to be $92,000, right? They would expect the average resale to be $92,000 in the long run. If they had this exact same scenario and they kept repeating it over and over and over again, they would expect to have an average sale price of $92,000. That's what the expected value is telling us. Now, that's not their profit. That's just what they can resell it for, okay? So we have to add to this, or we have to figure out what is the cost that they already put into it. Plus so that's how much they fixed it up with. So 50,000 plus 27 equals 77,000. So if they sell it for 92 and they put 77 into it, what could they expect for a profit?
About 50,000.
15,000. Okay. They would expect approximately $15,000 for their profit. Now, we have to know what they can sell it for, right? Because their costs in this particular case weren't selling. Well, we're talking about the model came from the sale price. That was the part that was changing. Okay? We understand where those numbers came from?
Not that,
Which part?
yeah, we take that.
The 15? Okay, so we have to just go back. We know we can sell the house for 92, but you have to go to the very first sentence and figure out, well, how much did they put into it first? 50,000 to buy it, 27 to renovate it. So they spent $77,000 and they're gonna sell it for 92. So it's just the difference.
Okay.
That's where the 15 comes from. So they earn 15, they profit $15,000 because it was positive, right? They didn't lose any money on that. Okay, other questions on that? So this is kind of what we're thinking about when we're talking about expected value, right? Another scenario I used to do had to do with like the insurance agency or life insurance, okay? Life insurance, and so there are actuarians who calculate probability, likelihood of death. Sounds like a fun job, right? But they have these probabilities associated with age, gender, you know, all of these things, and the insurance company will come through and figure out, okay, based on maybe what type of policy I want to offer, how much am I going to have to pay out? Because the likelihood that you actually have to use your life insurance policy is fairly low, and you pay for the life insurance policy over a long term. So the insurance money, right, the insurance companies are getting that money. And even if there was $1 million insurance policy, they've been accruing all of this money for the majority of people, say 97% of the time, let's say, And they really only have to pay out the $1 million policy maybe 3% of the time. Okay, but they use expected values like this to try to determine what the cost is of their policy. How much can they bring in before they're gonna have to pay out so that they can offset that, okay? All right, the last example we're gonna work has to do with the potholes. So we're gonna need, and I want y'all to follow along with me. So we need to be in StatCrunch, and if you go through Brightspace, go to our group and open up the data set that I put in there for section 6.1. Okay, does everybody have that data set pulled up? Okay, so we're gonna walk through some commands on how to do this in StatCrunch and how that's gonna look for us. So we have a problem there on your paper that says that the following data, right? The following data represents the number of potholes on 35 randomly selected 1 mile stretches of highway in some city, right? So they sent people out to look at 35 different sections of a 1 mile stretch and count up the number of potholes in that 1 mile stretch, okay? And this is the data that they collected. And so we know that when we see data like that, we're gonna put it into StatCrunch, which is what I've done for us right here, right? So that single column with potholes represents the data that we're looking at. Now, the question I'm being asked here is, what is the expected value? What is the expected value of the potholes? How many potholes in a 1 mile stretch could I expect to encounter if I am, I don't know, in this city? Well, what were the two components that I had to have in my model? I had to have a variable column, right? And what did I have to have next to it? The probability of that. So think about this for just a second. What's changing? What's changing in this scenario? What would our variable be? So if I go to this 1 mile stretch of highway, I might encounter 2 potholes, right? If I go to this stretch of whatever, I might encounter 3 potholes. I go over here, I might encounter 2. I go over here, I might encounter 1. What's changing every time I go to a different spot? The number of potholes. So the number of potholes becomes the variable, and I need to figure out what the associated probability is for each of those potholes. Now, rather than counting up how many stretches of highway had 1 pothole, how many stretches of highway had 2 potholes, and so on, what could I create instead? It's a table. What kind of table would I be creating? Frequency table, right? Okay, now, if I create a frequency table, I would go to Stat Tables Frequency. Choose my potholes. Now don't do it just yet. I just want to show you something. Right? So what have I found here? I don't want y'all to do this yet because I'm going to get you to do it a different way in StatCrunch, but I want to illustrate something here. What did I find? I let StatCrunch create a frequency table that showed me the frequency in which we found a stretch that had 7 holes, right? 7 potholes. And I let StatCrunch tell me how many of those stretches had 6 potholes, right? That's our frequency table. Now, how do I calculate the probability of encountering a stretch that had 7 potholes? What would I do? How do I find the probability of encountering 7 potholes?
Add them all,
Add what up?
all the frequencies.
All right, so there was 35, right? 35 stretches, okay? And then what?
Like 3 divided by,
7, because I'm talking about the set, or 3, no, you're right, 3, because there were 3 potholes, right? Or 3 times, there was 3 occurrences of 7 potholes, right? So I would take this number and I would divide it by the total, right? That's called what? What kind of table is that called? A relative frequency table. So in essence, if I come in here and I have StatCrunch create for me a relative frequency, then I have now created my probability model, haven't I? I created the probability model, which is what we're calling it now, which we learned in chapter 3 or 2, was really just a relative frequency table, wasn't it? Okay, so we're just recycling the same concept, just renaming it now, all right? So if I were to look at this, the probability, right? The probability of what's the probability or the likelihood that I'm driving through this city and I encounter a 1 mile stretch that had 1 pothole on it? What do we say?
31%.
31%, 0.314, okay? Right? Do we see that? That's up at the top, right? So the probability of 1 pothole is 0.314. The probability of 2 potholes would be 0.1423, right? Yeah?
Yeah.
All right, so relative frequency is the probability of the variable happening. Okay? The relative frequency is the table that we want to create. Now, on your paper, let's just round this thing down to 3 decimal places. I want you to recreate this table on your paper. You need a column that has the number of potholes, that's X. And we need another column that you're going to label P of X. Right, those 2 columns were given to us already in StatCrunch because they did the data crunching for me. Then you need to, let's round, and when you copy this on your paper, just copy it down to 3 decimal places, all right? So the first column would look like 1, 2, 3, 4, 5, 6, 7. Second column is going to look like 0.314, 0.143, and so forth. Now, the question that we're supposed to be answering here then would be the expected value, right? How do I find the expected value from the probability model that we see here?
Multiply X by P of X.
Right.
And then add them all together.
That's right. Now, there is no fancy way to do this in StatCrunch. You are simply just going to do it, right? You'll just have to manually do it. I'm just still in StatCrunch, so I'm just leaving it here, okay? So I want everybody to multiply the X column times the P of X column. And what happens when you add up that column? You there yet? What'd you get?
Two point five five one.
3.115. Yeah, that's good. 3.115. That's what we get when we add straight down, right? Now, this information here is our probability model. This came from StatCrunch, right? From the raw data. We had to manually calculate the X times P of X column to find the expected value. So the expected value is what? How would I interpret this in reference to this question, in relationship to this problem? How would I interpret that? What?
Isn't the expected value like the average?
Yep.
So is the average number of potholes?
Right? So say it in a sentence. Doing great.
Would be the average number of potholes on 7 different stretches of highway?
No. We got average in there though, or we would expect, right? But help her out.
I can try.
All right.
I guess it's the average number of potholes within a 1 mile strip
Is what?
is 3.1.
Okay, right? So we gotta include the number in there, right? Because otherwise it's not specific enough to the area we're at. Okay? Average is what we're finding. We might say, because what do we call this? This is expected value. So I'm gonna put that, I'm gonna work that into that sentence. We would expect approximately 3 potholes in a 1 mile stretch in this city. We would expect about 3 potholes on average, right? In a 1 mile stretch in this city. All right, did y'all need to write that down maybe? We would expect we would expect about 3 potholes on average in a 1-mile stretch of this city. We would expect about 3 potholes on average in a 1-mile stretch of this city. Now notice how I rephrased that, so when you have to, and I should have y'all's tests graded by this weekend, you'll know what that grade should be finalized on Monday. But when I give you a question like this, I just regurgitated the sentence, did I not? But it's specific, like what are we talking about? We crunched numbers on a 1-mile stretch of highway. So it's important that we refer back to this one, that we're talking about a 1-mile stretch of highway and not implying, right? Not leaving it up to the imagination to try to think of, maybe people think it's gonna be a 10-mile stretch of highway or whatever. We crunched data on a 1-mile stretch of highway, so that's what we wanna talk about. And we also wanna be specific by how many. You want to give the number, the expected value, right, of the potholes you would encounter on those 1-mile stretch of highways, all right? So those are the components that I would be looking for in here. All right, now, if we wanted to answer these other questions that you see there, right? So we'll come back to the standard deviation of this in just a minute. But for the next question, it says, what is the probability that a randomly selected highway has 2 potholes? What is the probability that my randomly selected highway has 2 potholes? Now the variable was X. The variable X was the potholes, right? So now look at how I'm fixing to write this probability statement. I want to know, what's the probability? What is the likelihood that my variable is 2? What's the probability that my variable is equal to 2? And we said that that was what? It comes from our probability model up there. What's the probability of my variable being 2? 0.143, that's right. That comes directly from my statement here. What if I said, what is the probability that I encounter a highway that has 5 or more potholes? Now look at my inequality symbol I just put up there. 5 or more. That means that the variable is greater than or equal to. I can have 5 or 6 or 7. Man, did you hear me say or in there? All right, so how do I find the probability then of 5 or more potholes?
Yeah.
We're gonna add them up. So that's gonna be 5, 6, and 7. And what do we find? Okay, is everybody able to see, oops, is everybody able to see where that came from? What if I said, what's the probability of more than 5 potholes? What would I do there? What's the probability of more than 5? Don't tell me the answer, just tell me what you would do.
Subtract 0.114.
No, good call though. More than 5.
You added the probability of
Which ones am I adding? I just can't hear you.
5, 6, and 7. The probability of
6
5,
and
6, and 7.
6 and 7.
6.
Because I'm doing more than 5, right? So I can't include 5, but I could have 6 or I could have 7, right? What's the probability? How would I find the probability of 3 or less? What would I do there? 1, 2, and 3, right? Because I can include 3. What's the probability of less than 3? 2 and 1. All right, so pay attention to the wording, whether I can include that value or not include that value. And remember that this symbol that I wrote up here, right, with that equal sign on the bottom, implies greater than or equal to. So 5 or more. Equal to 5 or more. Okay, so we are gonna be looking at a little math here. Okay, now how do we let StatCrunch help us out with this? And what do I do with that standard deviation portion that you see on your paper there? I'm never gonna ask you to calculate standard deviation in this class. So what do I do? Now, we are going to encounter today, I think on next week, and then we're gonna end up using 4 different calculators from StatCrunch in this class. So it becomes real important. I want y'all to all make sure you're making your list of all of your cheat sheets so it grows and grows for you as you move on to the final. One of the things that I would encourage you to do is put chapter 6, expected value, because we're going to use the custom calculator. Chapter 6, expected value, uses the custom calculator. So I'm going to go to Stat, select calculators, and custom calculator is down here at the bottom. Is everybody there? Stat, calculators, custom calculators is going to be at the bottom. That's what we're going to use for expected value. Everybody there? Stat, calculator, custom. Now, for this calculator, it wants to know what the values are in. The values are the variable, right? The values would be the frequency. So I relabeled mine as X, and their weights, right? What's the probability of that variable is going to be in P of X. Okay, so you've got to choose your variable column as well as its probability column. And when I hit compute, notice this calculator that comes up. There's a lot of stuff on this calculator I want to point out to you. Okay, does everybody get this pulled up? Make sure you can get this pulled up. Stat? Okay, so we're going to select, I labeled, click this drop down. You want the second one because you've got 2 potholes. Okay. And, okay, exit out of this. We need instead, just highlight and delete these. And let's redo it, okay? And go to Stat, tables. Let's rerun our table as a relative frequency. Relative frequency. And then store it in your table. Okay, so let's label this X, just so that when we see it, we're good. And we'll know that relative frequency comes after that. Now go back to Stat, calculators, custom. No, X is our value. So the weights or the probabilities. All right, did everybody get that pulled up? Raise your hand if you don't have that pulled up, if you need some help pulling that up. You have to go to Stat. So both of you go to Stat, go to tables, frequency. You have to choose potholes at the top. And we're going to choose a relative frequency in the center. And you store it in the table. So scroll down. No, I don't. Scroll down to the bottom to see store in table. Pick two. Who's there? Yeah. Okay, so now you have it in there. Now you're going to go to Stat, custom calculator, scroll to the bottom. The weights are in pothole 2. Yeah. The variable was in pothole 2. The weights are in relative frequency level. Hit compute. Go. right? Everybody got that? Okay. You want, all of y'all have it over here? Yeah? It's not potholes because the values are actually our variables. X will be P of X. We don't do anything there. They compute. There we go. Okay, notice that we have a graph. This is one of the things that I really like about this, right? Is that we end up with a graph along with the calculator. So if I'm looking at this, what kind of shape do I have up there? If you were to describe the shape of that graph, what would it be? Skewed right, correct? Skewed right. Yes. Now it looks a little different because it looks like just these little sticks, right? We're used to histograms having bars that are sitting next to each other. But this is what it's going to be represented as when we think about discrete variables, right? Because there's only one value, right? There's integer values, so they're not going to touch when they're being shown. Now, what do you notice here? The mean. Look at that number. How does that number compare to the one you calculated by hand? Same, right? That's awesome. It's the same thing. So the mean in this calculator is the expected value. The mean is the expected value. And like I said, I'm not going to ask you to manually calculate standard deviation. The standard deviation is calculated for us. Okay? So there's the mean. There's our expected value and our standard deviation that we're asked for. Okay, now the next part of this calculator that's fairly handy is this area here towards the bottom. Now notice it says, what is the probability? If I click that, that box and I get a drop-down menu here, I have all sorts of equality symbols, don't I? If we were to answer that first question we were looking at, what's the probability of getting 2 potholes? I'm going to change this to equals, and I'm going to change this to a 2. And when I hit compute, I should end up with the same answer that we had before. That's the same thing we got before. Now, does everybody notice why maybe I've been harping on you to write your probability statement as such? Right? All of a sudden, if I have been writing on my paper when I read the instructions or when I read the question, and I'm trying to figure out what's the probability, capital P, of X equal to 2, I can see whether I'm doing it right, right? I know what I'm doing. Take some stuff out of your head and actually put it on a piece of paper, right? You'll make less mistakes that way. So here on these 2 blanks on the left, right, that's the probability of our variable happening, whatever we're looking at. Or that's not the probability of it happening, that's the question we're asking. The one on the right, this blank on the right, the 0.143 blah, 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 is the probability of it happening, okay? And when you come to a test for me, when we come through and we do a lot of these types of calculators, students start to get kind of confused in this area down here. I don't care if you if you sketch that for me and draw, you know, mean is expected value. The blank down here on this far right is the probability of the variable happening. I don't care if you do that, right? That's just you denoting how to use the calculator, okay? So we've got our probability equal to 2. What was the next question that we had? So I'm going to come in here and I'm going to select this and I'm going to choose the inequality symbol for greater than or equal to, right? Greater than opens up towards the variable, okay? Change my 5, hit compute. We should get the same number, 0.257. So it's a calculator, it's doing it for us, right? But we've walked through the process, and we can also do it by hand should we need, okay? But this is the custom calculator And we will be using another calculator, a different calculator, when we come to class, I think on Tuesday of next week. All right? The between, can't remember if there are any between in there. But if you click the between one, notice what it did down there in the P of statement. It says, what's the probability of a 2 or a 3, right? What's the probability of my variable being between two numbers? That's all that's saying. Okay, so the between, notice that my hand is still sitting up there, right? If I click the between, then I have this statement here. So maybe I want to know what's the probability of finding potholes between 2 and 5, right? That would be the range I would be looking at, okay? Okay, are there questions on this? No, you all wrote down how to get here. You all know how to get back to this, okay? Now remember, StatCrunch does not create that table of X times P of X, right? You create that by hand by multiplying that. In essence, StatCrunch is doing it individually, aren't they? Okay, StatCrunch is calculating each of those individual cells. But if I wanted to ask you to do it for me in a single column, that's how you would do it. Would multiply it by hand, right? StatCrunch can create the relative frequency table if I'm not given one. If I'm not given the raw data, StatCrunch can't give me a relative frequency table. I would have to add up, right, the totals and divide each of the cells to get the relative frequency of each of the values that we're looking at. Okay? All right. You don't have any questions, then I'm done today. You have homework over this material as well as